Hello student, welcome to the ROSE project 12th Standard Science which is conducted रे शिक्षण संस्था Sadhguru Kadge Maharaj College Karad. Myself Hasbe SS, subject physics, topic number 11, magnetic material. In this topic we firstly introduction of magnetic material. Second one, torque acting on a magnetic dipole in a uniform magnetic field. Second, last one, origin of magnetism in a material. Firstly, look at introduction. In previous standard, we discussed all these points. Firstly, magnetic dipole. Magnetic dipole, the two equal and opposite magnet poles are separated by a small distance. Second one, magnetic dipole moment, product of a pole strain and length of the magnet. What are the magnetic material? A magnetic material is a material that experiences a force when placed in a magnetic field. Although all magnetic material are metallic, not all metal are magnetic. Common magnetic material included iron, steel, nickel, cobalt. Note here, copper and aluminum are not magnetic. Now second point we discuss here, torque acting on a magnetic dipole in a uniform magnetic field. I am firstly showing the figure here. Now torque on a bar magnet placed in an uniform magnetic field. When we can define couple as a pair of two equal and opposite force having a different line of action, they gives rise to turning effect known as a torque along the axis which is perpendicular to the plane of force. The torque acting on a rectangular current carrying coil kept in a uniform magnetic field is given by torque bar is equal to mb cross b bar. Torque is equal to mb sin theta, where theta is angle between the m and b. The force exerted on the pole of the bar magnet due to the magnetic field along the different line of action, this force form a couple. The couple produce a pure rotation motion along to the rectangular angular magnetic coil in a uniform magnetic field. The bar magnet will follow the same equation. The torque is equal to mb sin theta. When the electrical dipole is kept in the electrical field, that means here store of the energy, and this store of energy is known as the potential energy, means magnetic potential energy. In this point we also discuss about the magnetic potential energy. Whenever displacement is taking place, the work is beginning done, and such a work is stored in the form of potential energy in the new position. The potential energies of a bar magnet in a uniform magnetic field is taken to the um is equal to integration 0 to theta torque delta theta. Therefore, is equal to integration 0 to theta means value included torque here mb sin theta delta theta, and sin theta integration of sin theta is convert to the minus cos theta. That means given to here equation of potential energy is equal to minus mb cos theta. Now nextly here discuss about the position of potential energy and given to the three cases. Firstly, case 1, when theta is taken to the 0 degree, then cos theta is equal to 1, and potential energy is taken to the minus mb. This is the position when m and b are parallel and the bar magnet possesses minimum. The potential energy is in the most stable state. Now second case, cos theta is taken 180, that means given to minus 1, and a potential energy is taken to here mb, and this is the position when m and b are anti-parallel. and bar magnet possesses the maximum potential energy and thus is in the most unstable state. And last one case is number 3, when theta is equal to 90 degree, that means cos 90 degrees is equal to 0, and potential, and therefore also potential energy is taking to the 0, and this is the position when bar magnet is perpendicular to the direction of the magnetic field. Look at the figure here, arranging the theta. Firstly, figure sign here, theta is equal to 0 when torque is given to the minimum, and this is potential energy is a minus mv and stable equilibrium state. Now secondly, we have to discuss theta is equal to pi by 2 means 90 degree. Cos 90 degree is given to the 0 and potential energy is a 0, and this bar magnet showing the figure. And last one, theta is equal to 180 degree and torque is equal to 0 and potential energy is maximum, means given to the mv, and the state is your mostly unstable state here. As showing also graphically presentation, potential energy versus angular position of the magnet, and the potential energy as a function of theta is given here, figure this one. Now nextly you discuss also included point here. Suppose the bar magnet is suspended using the extensible string. When observed that the magnet rotate through angle and then become stationary, this is happen because of the restoring torque. In this strings opposed to the deflecting torque in the equilibrium, both the torque balance. Therefore, the torque is equal to I d square theta by dt square, and the action of the torque acting on the magnetic is clockwise. Now, if one tries to rotate the magnet anti-clockwise through an angle delta theta, then there will be the restoring torque acting as given by the equation. The opposite in the opposite direction, thus we written as restoring torque is equal to minus mb sin theta, and from the two equation we get I d square theta by dt square is equal to mb sin theta from previous equation. When the angle displacement theta is very small, therefore the sin theta approximately theta, and the above equation we can written as the I d square theta by dt square is equal to mb theta, and d square theta by dt square is equal to minus mb r by theta. Simplify this equation, and this equation has an angular acceleration on the left hand side and angular displacement theta on the right hand side of the equation, with m, b and I being held constant. And this is the angular simple harmonic motion along to the linear simple harmonic motion governed by the equation d square x by dt square is equal to minus omega square x. This is the previous chapter we discussed about that, and given to the equation of the d square x by dt square is equal to minus omega square, and this known as the chapter number 5. Here omega square is equal to mb by I. Therefore, omega is equal to square root of mb by I, and the time period of the angular oscillation of the bar magnet will be torque will be T is equal to 2 pi by omega is equal to 2 pi square root of I by mb. Now next point here discuss about origin of magnetism in the material. In an atom, negatively charged electrons are revolving about the nucleus of the electrons orbit in the outermost orbit. In this point, subpoint is given magnetic moment of an electron revolving around the nucleus of an atom. Showing you firstly figure here, single electron revolving around to the nucleus. Consider consider an electron moving with a constant speed v in the circular orbit of a radius r about the nucleus as shown in a figure. An orbit is equivalent to a tiny current loop. The magnetic dipole moment due to a current loop is given by m orbit is equal to Ia. Magnetic moment of an electron revolving around the nucleus of an atom. M orbit, last point here given the equation, M orbit is equal to Ia. A is the area included by the loop and I is the current. It is only a part of the magnetic moment of an atom and is referred to as the orbit magnetic moment. An electron possesses an instant angular moment and the spin angular moment. Spin magnetic dipole moment result from this spin. Consider an electron moving with the constant speed v in a circular orbit of a radius r about the nucleus as shown in a figure below. If the electron travel a distance of 2 pi r, that means circumference of circle, in a time t, then its orbit speed v is equal to 2 pi r by t. Thus the current I associated with this orbit IE by t is equal to 2 pi by omega, and omega is equal to v by r, the angular speed. I is equal to e omega by 2 pi is equal to ev by 2 pi r. The orbital magnetic moment associated with the orbital current loop is m orbit is equal to Ia is equal to ev by 2 pi r into pi r square is equal to half ev for this electron's orbital angular moment is equal to mevr, where me is the mass of an electron. Hence the orbital magnetic moment equation above we can written as m orbit is equal to e by 2 me into mevr. Therefore m orbit is equal to e by 2 me into l. This is equation show that orbital magnetic moment, but as the electron negative charge, the vectors m orbit and the l are in opposite direction and perpendicular to the plane of orbit. Hence vectorially m bar orbit is equal to minus e by 2 me l bar. The same result in obtained using the quantum mechanics. The ratio e by 2 me is called gyromagnetic ratio, and for an electron revolving in a circular orbit, the angular moment is an integral multiple of h by 2 pi. From the second postulate of a Bohr theory of hydrogen atom, L is equal to m evr is equal to n h by 2 pi. Substitute the value of L in equation above, we get m orbit is equal to ENH by 4 pi me. For the first orbit, n is equal to 1, giving m orbit is equal to EH by 4 pi me. The quantity EH by 4 pi me is called Bohr magneton. The value of Bohr magneton is 9.274 into 10 raised to minus 24 ampere per meter square. The magnetic moment of an atom is state in term of both magnetic tones mH. Thank you.